The elimination method is probably my most favorite method for solving systems of equations. Unless our equations are set up otherwise, usually when they're in standard form, this is the easiest way for me to solve them. So I'm going to show you how I solve systems of equations this way. 5x minus 6y equals negative 32. 3x plus 6y equals 48. When we solve by elimination, we want to add or subtract the equations so that we can eliminate one of the variables. That's going to create an equation in one variable. So I have two equations here, equation 1 and equation 2. If I can simply add the two equations together and one of the variables has additive inverses for their coefficients, negative 6 and positive 6 are additive inverses of one another, meaning when we add them together, if I were to add equation 1 to equation 2, I would be left with 8x equals 16. 5x plus 3x is 8x. Negative 6y plus 6y, those are additive inverses, that zeroes out. Negative 32 plus 48 is 16. Notice how the equal sign is still lined up. So our constant is on the right. We divide both sides by 8 and we get x equals 2. This is half of our answer. Now we just have to find our y value. And you probably suspected by now that we can just simply substitute x equals 2 into one of our equations and solve for y. 3 times 2 plus 6y equals 48. This is 6. 3 times 2 is 6. Subtract that from both sides, and we get 42 on the right-hand side. That does not want to go away. That was like permanent for a second there. Divide both sides by 6, and we get y equals 7. So our answer is the ordered pair 2, 7. X equals 2 and y equals 7. Let's try the next one. The next one's interesting, not just because they both happen to have additive inverses that are 6's again, but this time, when I add the two equations together, the additive inverses this time are attached to y, not y, x. Y is going to be left behind. So the 6's get eliminated from the x's and the y's do not. So 6x plus negative 6x is 0. Negative 3y plus 5y is 2y. 2y equals 6. We get y equals 3. Keep in mind that the y is the second value in the ordered pair. So we're going to take that 3, we're going to put it back in to one of the equations in place of y. 6x minus 3 times 3 equals 3. Well, that would be minus 9. If we add that to both sides, we get 12. And x equals 2. And that's our solution. Here's one for you to try. Go ahead and press pause, and when you come back, I'm just going to be able to provide you with the answer, and I think we'll be ready to move on to some more challenging problems. Okay, welcome back. We're checking your answer, and the answer is, I think it wanted me to reset for a second there. The answer is, drum roll, 7, 3. So if you got 7, 3, you got it. So how can this get any more challenging? Because it seems like it's really not too bad. Well, we can have an example where our additive inverses aren't already set up for us. So we have 2x and 10x. If I add those together, I get 12x. 5y and 3y. If I add those together, I get 8y. So nothing's getting eliminated. So what I have to do is I have to force either the x's to have additive inverses or the y's to have additive inverses. Well, equation 1, we'll call the first one on top, and equation 2 is the second one just below. If I take equation 1 and I multiply it by a negative 5, equation 1 would become negative 10x minus 25y equals 110. The second equation would remain the same, 10x plus 3y equals 22. And now if I add the two equations together, the x's are eliminated. I have negative 22y equals 132. 22 goes into 132 6 times, so that would be negative 6. Now I'm looking at the original equation, 2x plus 5y equals negative 22, and I'm going to substitute in for y a negative 6. 2x plus 5 times negative 6 would be negative 30 equals negative 22. We add 30 to both sides, 2x equals 8, and x equals 4. So the answer is 4, negative 6. Now here's another example. 4x minus 2y equals 12. 5x minus 4y equals negative 6. I have equation 1 and equation 2. If I want to eliminate the x's, I'd have to do some pretty creative multiplying. If I want to eliminate the y's, I can see a little bit more easily that I can multiply the first equation by a negative 2 so that I have additive inverses for the coefficients of y. So the first equation will become negative 8x plus 4y equals negative 24. The second equation remains the same, 5x minus 4y equals negative 6. We add the two together, we get negative 3x equals negative 30. Divide both sides by negative 3, and x equals 10. I'm going to go back to the first equation. In place of x, I'm going to put 10, which allows me to solve for y. I'm going to subtract 40 from both sides, which gives me negative 28 is equal to negative 2y. Y is equal to 14. So our answer is the ordered pair 10, 14. Now what happens when we can't easily just multiply one equation to get additive inverses? So you can see here I can't multiply anything times the first equation to get a 7 without going into fractions. And on number, same problem. But when I look at the y's, I can't multiply one equation without going into fractions to get additive inverses for the coefficients of y. Therefore, we're going to multiply both equations. So this is an example of multiplying both equations. I think of it as getting a common denominator in sorts. So if I wanted a common denominator between 4 and 7, that would be the number 28. So I'd have to multiply 4 times 7, and I'd have to multiply 7 times 4. If I wanted to eliminate the y's, I'd have to have a 6. 2 times 3 would give me 6. 3 times 2 would give me 6. I want to have additive inverses. Remember, additive inverses is when one is positive and one is negative. So we're going to multiply the first equation by 3, which will give me a 6y. And we're going to multiply the second equation by 2, which will give us a negative 6y. I'm going to erase that. If you need to play that again, you're more than welcome to do that. I'm multiplying the first equation by 3 and the second equation by 2. The first equation becomes 12x, 3 times 4x is 12x, plus 6y equals 36. Don't forget to multiply every term by 3. The second equation becomes 14x minus 6y, there's our additive inverses, equals negative 16. I add the two equations together, 26x equals 20. Divide both sides by 26. Reduce, and I get 10 over 13. So the first part of my ordered pair is 10 over 13. Now I can take that 10 over 13 and plug it into one of my equations, or I can do this whole problem again, eliminating the x's. So I'm going to show you that we can do that. I'm going to take the original equation, 4x plus 2y equals 12, 7x minus 3y equals negative 8. I'm going to multiply the first equation by 7, and I'm going to multiply the second equation by negative 4. That's going to give us 28x. Let me do this color coordinated first. The first equation becomes 28x plus 14y equals 84, and the second equation becomes negative 28x plus 12y equals 32. We add the two together, 26y equals 116. Divide both sides by 26. Reduce by 2, and we're going to get 58. 58 over 13. 58 over 13. Now here's one for you to try. You go ahead and try it, but I'm going to show you, when you come back and check your answer, I'm going to show you something pretty creative. Pretty creative. Okay, press pause, work on it, and then come on back. Okay, long story short is the answer is negative 2, 2. So if you got that, fantastic. But let's see if you got it the way I got it. Now what I noticed about this first equation is that all of the coefficients in the constant are divisible by 6. So that gives me an equation, negative x plus y equals 4. And then I noticed the second equation, well, that was all divisible by 5. So that gave me negative 2x minus y equals 2. And now I naturally had additive inverses. Negative 3x equals 6, x equals negative 2. I feel really, really confident that I divided properly. So when I put my value back in for x, I'm going to put it back into this smaller equation with smaller numbers. The opposite of negative 2 plus y equals 4. Well, that's 2 plus y equals 4. Well, y has to be 2. 2 plus 2 is 4. And that's how we get negative 2, positive 2. Now let's summarize up what happens when we have those infinitely many solutions and no solution. When you solve algebraically, if all the variables go away and you have a true statement such as 0 equals 0, or maybe 5 equals 5, no variables, yet true. True and no variables. Both cases. 5 equals 5. That's the same thing. True, but no variables. That means that the lines are coinciding. The lines are coinciding. And when the lines are coinciding, you have infinitely many solutions. Infinitely many solutions. If the variables all go away and you have a false statement, such as 0 equals 4, that's false. Or 0 equals -3, that is also false. Then the lines are parallel, meaning there is no solution. No solution. So as you're solving systems of equations, the better you get at solving them all three ways, the better you'll be at deciding which way is the most efficient way to solve a given system of equation.